Okay, so look at, okay, so we're trying to compare the acid strength of this chemical and this chemical. Okay, so you want to draw their approximate Lewis structures. And remember, when you have an oxyacid, the hydrogens are always joined to the oxygen. Okay, so I've marked the acid hydrogens in red. And then you knock off the acid hydrogen, and the name of the game is to figure out which of these is going to be the more stable conjugate base. Okay, now these oxygens are stuck with a negative charge. The question is, how can the rest of the molecule spread that out? Okay, you might recall that oxygens will pull electrons away. Now, this carbon has two oxygens on it, so you might think it has the advantage. The problem is, remember, hydrogen donates electrons. So in a way, hydrogen and oxygen cancel each other out. So if you neglect this, you'll notice that both the central atoms have one extra oxygen on them. So it looks like it's a tie. So what breaks the tie? You have to look at the electronegativity of the central atom. Okay, so the question is, who pulls harder on shared electrons, carbon or nitrogen? Okay, now I was hoping, can you see my shirt? Because I purposely wore this periodic table. Okay, if it doesn't show too well, if you look on the table, you notice that nitrogen is closer to fluorine than carbon. So nitrogen pulls harder, therefore it's going to pull the electrons away, making this the more stable conjugate base, so this would be the stronger acid. Can I go on to the next one? Okay, is that all right?
Yeah.
Okay, here was the next homework problem I gave you. Again, am I holding it high enough? Can you see it okay? It should be H2SO3 versus H3PO4. That's the competition there.
You might want to raise it just a little bit.
Raise a little bit. Okay, is that better? You know, also, I wonder if I turn my computer screen, does that make any difference?
Yeah, that's better.
Okay, so if I lower this, then it's okay?
Yeah.
Okay. Okay, so it's a competition between H2SO3 and H3PO4, which is stronger acid. Again, you want to draw the approximate Lewis structure. I'll give you a chance to take a picture of it or at least copy it. So remember, what happens is the oxygens are going to spread around the central atom, and the hydrogens are going to be attached to the oxygens. Then you want to knock off one of the hydrogens. I marked them in red. That'll be the acid hydrogen. And now the name of the game is to look at the stability of the conjugate bases. Now remember, oxygens will pull electrons away. So if you look at the top one, it has one extra oxygen. But then remember, O and H, they cancel each other out. Okay, so you want to count the top one as having one extra oxygen helping. Now if you look at the bottom one, again remember, OH is a tie, so it doesn't help or hurt. The top one, the bottom one also has one extra oxygen. So it looks like it's a tie. They both have one extra oxygen helping. So what's going to break the tie? The electronegativity of the central atom. So phosphorus versus silicon. Anyone have a periodic table handy? I've got one on my chest, but I don't know if you can see it very well. Okay. If I remember correctly, I think phosphorus is closer to fluorine than silicon. So phosphorus would stabilize the negative charge on the oxygen more than silicon would. So the bottom one would be the stronger acid. Okay to go on? Polly, I'll make you the class spokesman. Okay to go on, Polly? No response, huh? Luke, are you okay?
Yeah, I'm good.
I'll go on to the next one then. Okay, here's a summary chart that may help you on this topic of structure versus strength. Okay, you can break acids into two types, oxyacids and binary acids. Okay, the oxyacids are always one where you have the central atom and then you have OH. The binary acids where you have a central atom joined to hydrogen or many hydrogens. Okay, now here's the trend in terms of oxyacids. Think of X as pulling electrons away from the oxygen. The better it pulls, the more stable the conjugate base. Well, fluorine would be the champ. So it means if X is closer to fluorine, it has a higher electronegativity and makes it more stable. So there's an increase in acidity as you go across the table, getting closer to fluorine, or if you go up a family as you get closer to fluorine, it increases acidity because it'll stabilize the charge on the oxygen more. So that's a nice trend for oxyacids in terms of the periodic table. Binary acids is a little more complicated. Okay, in the case of binary acids, okay, when you lose a hydrogen and put a negative charge on atom X, okay, as you go down a family, the acidity increases because of size. As X gets bigger, it has a smaller charge density. Now, as you go across the periodic table, notice that the molecules will have fewer hydrogens. See, hydrogens are bad. They donate electrons to the central atom. So as you go across, you have fewer hydrogens. The acids become stronger because you have fewer hydrogens donating electrons. For example, HF only has one hydrogen. If you lose that, F has the charge on it. H2O, if you knock off the acid hydrogen, only has one hydrogen donating, which is better than having 2 or 3. So this is a trend for binary acids. So that's kind of a nice trend that might help some of you figure out the strength of acids.
Sir?
Question?
What did it say up on the top? The acids?
Oxyacids?
Oxyacids. Thank you.
An oxyacid is one in which you have the hydrogen is joined, the acid hydrogen joined to an oxygen, and then you have the rest of the molecule.
Can you read what
Okay, go on.
acid? Or for, I'm sorry, for the binary acid?
And for the binary acid, the trend is as you go down a family, the acids become stronger. As you go across the table, the acids become stronger.
What do you have written next to the X?
Means increase in acidity.
On the top, next to the
On the
X.
top, increase. And these are different molecules. As you go across, this is what the molecules look like for binary acids. So this would be CH4, NH3, H2O. So as you get across, the molecules have fewer hydrogens, which is good because hydrogens donate electrons, which is bad. So the fewer hydrogens you have on the molecule for binary acids, the stronger the acid. What do you think, Amanda? Seem okay?
If it's no hassle, do you mind posting the picture in the chat as you did so that those of us who can open the chat can see it? Or
Sure.
all right, thank you so much.
We'll try, give it a try, see how it works on.
All right, however you did it last time works for a couple of
Okay,
us.
so let's see. The first one I showed you was this one. Can you see that one?
Yeah.
I'll probably have to hit click to open. Let's have to find it. Let's see here. So that was the first one. Is that helpful, Luke?
Yeah, we got the first one, and then
Okay, now I'm going to go on to the second one.
all right. All right, there we go.
Okay, that one shows okay?
Yeah, that one shows perfectly. Thank you.
Okay. Okay, now you want the trend, right?
Yeah, that would be awesome.
Okay, so this one's called...
All right, perfect. Thank you.
Is it working for more than Luke?
Yes.
Yes.
I got it.
Yes,
It's working for me as well.
That's the trend one. Okay? So I'll do it both ways from now on. I'll hold them up by hand and then I'll also do this, okay?
Thank you.
Okay, here we go. Okay, here's our next topic. Okay, you remember K sub A of an acid means they give you the formula for the acid, and an acid's going to break off to give us acid hydrogen and the conjugate base. Okay, so this is what K sub A abbreviates. That's a K sub A reaction. Now, in reality, what it really means is you take the weak acid and put it into water, and it undergoes a Bronsted acid-base reaction. The weak acid gives the hydrogen to water, becomes hydronium. Hydronium is really the truth about an acid hydrogen, and you get the conjugate base. Now, most of the time in chemistry, we can get away with this picture, even though this is the truth. Luke, should I also do?
In the chat, yeah, that would be wonderful.
Okay. Anyone else need time to copy this down, though?
Yes,
Okay,
please.
let me go to the chart. Does it show okay?
Yep, it shows perfectly. Thank you.
How long should I leave it there?
Once you post it in the chat, we can see it at any time.
Oh, okay. I'm curious. Why don't you yell out if you can't see it? I'm just kind of curious who cannot see that.
I can't see it.
Yeah,
I can't see it either.
Okay, but some of you can see it. I'll be able to get it hopefully by hand. Okay. Now, here's the reason I showed you K sub A. We're now going to study K sub B. Okay. Now, when it comes to K sub B, you have no choice. You must add water to the base. So carbonate's the base, and you put water in it, then do a Bronsted acid-base reaction, and notice what happens. You're going to get the products are HCl3 minus and OH minus. Okay, that OH minus is the tip-off that you've done it correctly, because if it's really a K sub B reaction, you should get hydroxide as one of the products. So this is what a K sub B reaction looks like. They've named the base for you. You put it in the water and you do a Bronsted acid-base reaction. Now, copy the one below, because in a moment I'm going to ask you to write the K sub B reaction for the one on the bottom. Anna, are you okay as far as getting that? Okay, now for those of you that can't see it on your screen, I'm going to hold it up by hand then. So, Anna, is it okay to go on?
Yes, thank you.
Okay. Anna, I like your hat. Okay. So, again, if you couldn't see the other one, let me talk you through on this. So a K sub B reaction goes like this. We name the base for you, then you put it into water, and you do a Bronsted acid-base reaction. So remember the Bronsted reaction, the acid gives a hydrogen to the base, so the products are HCl3, and then the water becomes hydroxide. If you've done it correctly, you should get hydroxide as one of the products. Now, let me give you a moment to try this one on your own. Write the K sub B reaction for this chemical here. The chemical is C6H5NH2. So we're giving you the formula for the base. Your goal is to put it in water and see if you can write down the products.